Alright, so we're going to talk about the Fundamental Theorem of Calculus, part 1 here. Now, the Fundamental Theorem of Calculus states something that may not be initially intuitively obvious, but it states that there's this sort of unexpected relationship between the derivative and the integral. Unexpected for me, at least, because I would never have thought that the slope of a curve and the area under another curve would have this sort of inverse relation. Isaac Newton might have, though, because he discovered it a while ago. But there's a few different ways to understand this connection, and I haven't found one that's like super clear. But let me give you one way that might help understand a little bit, and I'll see if it helps. So basically what the theorem says is that we have, if we define g of x as sort of the integral of f of t, or in this case, this is sort of the area so far function, area between 0 and x as we move x along, then g prime of x equals f of x, meaning that f of x is, if we define g of x as sort of the area under f of x, then f of x is the slope of g of x. So bizarre connection, but let's see if we can kind of piece together why this might be the case. So suppose we have this function here. This is our f of x function in the blue. Now, what I mean by g of x, or this area under the curve function, let me show you a little video to help see if we can explain this. So here we have the green. This blue is our function f of x, and the g of x is what I'm going to call in purple here. It's this area under the curve, and as x moves along, you can see that we're getting more area under the curve in this purple. There's going to be more purple area here, and this value here, g of x, is going to get bigger. So this is sort of what we mean. See, as x is getting bigger, g of x is encompassing more of that purple area, and g of x, the value for g of x is getting bigger. Here's g of x here shown in the purple. So the blue is the f of x, and now the purple here is g of x. Now, just bear with me here a minute and say that if this purple area is g of x, then let's just add a little bit to x, call it x plus h, and find the area under, we'll find g of x plus h. So we're going to show that in orange here. So g of x plus h is just a little bit more area. We're just going a little bit further. Instead of just going to x, we're going to x plus h. So you can see we're going to add a little bit. Now, I'm going somewhere with this, but let's just say that we wanted to find the difference in these two areas. So by the difference, if you wanted to basically subtract the purple area from the orange area, we could make it sort of an estimation for that. And we could call it like this area in the red here. It's sort of like that difference, that delta between g of x plus h and g of x. And this is just an approximation, right, because it's just a rectangle. But it's decent, given that h is relatively small. It's a decent approximation. And if we wanted to find the area of this, that wouldn't be too hard. The area in the red, that's h times f of x. Now, bear with me a little bit, and we're just going to combine these into one equation. So let's first of all take this area in the orange, or g of x plus h. And we're going to subtract from that the area in the purple, or g of x. And of course, when we did that, we found that was approximately equal to a, which was h times f of x. So if you're with me so far, thanks for hanging on. So basically, now that we got here, we can just manipulate this equation a little bit and show you what we're how this correlates to the fundamental theorem of calculus. So all we need to do is divide by h on each side, manipulate this equation a little bit, and we get g of x plus h minus g of x over quantity over h is approximately f of x. Now, hopefully at this point, maybe you need to look at that for a little bit and see if that value on the left, if that equation on the left rings a bell for you. It hasn't been too long since you've taken differential calculus. Hopefully you recognize that as something like the limit definition of the derivative. If you recall back, in differential calculus, we found that the limit, so as h approaches 0, as h gets really small, then that formula that we found is equal to the derivative of g of x. Now hold on, earlier we were just talking about f of x, and now we're actually equating this to the derivative of g of x. So you can see that that formula equals the derivative of g of x, but it also equals f of x. And now we can actually say it equals f of x because when this h gets really small, then this area in red here turns out to be, when h gets really small, it is exactly the difference between our orange and our purple areas. So now we have an exact relationship here, and we can say that the derivative of g of x is in fact f of x. So what does it mean that g prime of x is equal to f of x? Well, it might help to plot out g of x just to see what we're actually saying here. So g of x is shown in the purple up here by this purple area, but we can also plot it out. So here you can see we have plotted out g of x as the red curve, and the value in red at each of these points indicates that the amount of area in purple at that x value. So the red is our g of x function if we actually plot it out on the same plot here. Now we're looking at g prime of x, of course, so that's going to be the slope. So to find the slope, we can look at the rise over run. So if we look at this point at sort of this area towards the left here, we see that it looks like we have about a rise of about 3 over a run of about 1. So we could say that our slope here of g of x, or g prime of x, is approximately 3. Now what we just found here is that that g prime of x is actually equal to f of x. And remember, f of x was the blue function that we were taking the area under. So, and you can see here that in this region, f of x does actually equal approximately 3. So this is what the fundamental theorem of calculus is telling us, and bear with me for a minute. So if we have a function, as we show here, f of x in the blue here, if we have a function and we take the area under that function as a function of x, and then we take the slope of that area of the function, that slope will bring us right back to that initial function. So again, if g of x is the area under a function f of x, then f of x is the slope of g of x. Now this is the fundamental theorem of calculus, because what it does is connects differential calculus to integral calculus in this sort of bizarre, unexpected way. And it's called the fundamental theorem of calculus because it just so happens to be the fundamental theorem of calculus, which, as you may imagine, makes it pretty fundamental to calculus.